Okay, hi. So we're going to continue looking at convergence tests. Just very quickly recap what we did yesterday. Yesterday, we started off by proving theorem 2.2, which was a nice property of convergence for series. We showed that if you had two convergent series, sum of AM and a sum of BM, so two convergent series, then when you create a new third series by taking a linear combination of corresponding terms from the first two series, then this new series is also convergent. Okay, so forming linear combinations of series preserves convergence. It keeps the thing convergent, and the new series has it doesn't have some totally unrelated sum compared to the previous two. It has the very obvious sum that parallels the way the new series is constructed. So the limit of this new series will be alpha times the limit of the first sequence plus beta times the limit of the second sequence. Okay. So we proved that. We showed how that followed from the way we've defined convergence for series. And what else did we use? We also used the similar result for sequences, the result about taking linear combinations of sequences. Okay, we used that as well. Okay, if you weren't here, you can see the proof of that. If you look at the recording of yesterday's lecture, in the comments to it, you'll see my scanned pages there. Then we also proved the first of our convergence tests. So just very briefly, these convergence tests, which begin on page 14, 15, 16, they're a collection of tools, if you like. And given any series, one or more of these tools may be applicable to the series. You may be able to use one of these tools, one of these convergence tests, and the test might be able to tell you whether or not that series converges or diverges. Okay? There's different tests which are applicable to different types of series. Typically, the test sometimes allows you to say the series converges, sometimes diverges. Generally, they don't tell you what the sum of the infinite series is going to be, except for the one special case of geometric series, which we're about to discuss. And well, we proved the first of these convergence tests yesterday, and this was the test which said, well, there's two equivalent ways to present it. We proved this second way. It said that if you have a convergent series, if the sum of AM converges, that implies that the terms of the series must be converging to zero, considered as a sequence of terms. The terms themselves must be getting smaller and smaller and vanishing. Any convergent series must look like that. Now, it's not saying that every series whose terms converge to zero is a convergent series. Okay, we had our key example of the harmonic series. This is a series whose terms converge to zero, but it is still divergent. So it's not enough. Having your terms converge to zero is a necessary condition for convergence, but it's not sufficient. We often talk about necessary conditions and sufficient conditions in mathematics. So having terms converging to zero is necessary to be convergent, because if you're convergent, you have to have terms converging to zero, but it's not sufficient because the harmonic series has terms that converge to zero, but that's not sufficient. That's not enough to say that it converges, okay? So the harmonic series still, it diverges. But looked at it, flip it around and look at it from the other direction, you can also use the test that says, well, if you're looking at a series which has terms that don't converge to zero, if the terms of the series converge to some non-zero limit, then you know the series is going to be divergent. When you wait around long enough, the terms of the series will be getting closer and closer to this non-zero limit. So the series will more or less be behaving like adding repeated copies of that limit together, approximately. And if you have some non-zero quantity and you're just adding it up, repeated copies of it without end, that's clearly going to be divergent. Okay, so let's continue on and look at our next test. So the next test is the geometric series test. And I'm going to describe this on pen and paper. So this, well, there's the statement of the test there. You can read it. The geometric series, this applies to series which look like this. And if you run out the first few terms of this, this is a plus ar squared plus ar cubed, etc., etc. Okay, adding up all these quantities without end. So it has some initial term a, and then each subsequent term is obtained by multiplying the previous term by r. So r is this common ratio term, and a is the initial term of the series. Now, the geometric series test here in Theorem 2.4 gives you the complete story about these in terms of a and r. Okay, it's a complete description. It says, well, okay, we'll just read it, and then we'll go through and explain it and justify each of these conclusions. It says it converges trivially if a equals 0. If a is non-zero, then it converges if and only if the absolute value of r is strictly less than 1. So there where it says it converges if and only if absolute value of r is strictly less than 1. That means if the absolute value of r is strictly less than 1, it converges. If it's not strictly less than 1, i.e. the absolute value of r is greater than or equal to 1, then it's going to diverge. Okay? So it converges if and only if this inequality holds. So if this inequality doesn't hold, therefore it diverges. And nicely, and this is kind of unique amongst the convergence tests we're going to look at, it actually gives you a formula for what the sum of the infinite series is. A over 1 minus r. So in the cases where it does converge, that is what the sum is going to be. Okay. So let's deal with all of these things and explain them. So the first, well, there are some trivial cases to deal with. If a equals 0, this is kind of like the most boring series you can imagine. Because what is it equal to? Well, it's just 0 plus 0 plus 0 plus dot, dot, dot. Okay. So that is equal to 0, clearly. You're just adding up 0 without end. You never go anywhere, okay? So it's nothing to scream or shout about, okay? It's quite trivial. So that's what it means when it says it converges trivially. It's trivial that it converges. It's not interesting at all. It's not really a genuine geometric series. Also, we can assume, so we assume now that a is not 0. Because we've dealt with the a equals 0 case, so now we just have to deal with the case where a is not 0. Well, again, there's another kind of, well, there's a few trivial cases now. So some more trivial cases to deal with. Maybe not so trivial, but still kind of trivial. If r is 0, again, it's nothing to scream and shout about, because then it's going to look like it's going to be a plus 0 plus 0 plus 0. Okay, every term after the first one has an r in it, so you're just going to be left with a. So it's going to be convergent because it has a sum a. But again, it's kind of trivial convergence because it's mostly 0. If r is 1, then the series looks like this. It's just a plus a plus a plus a plus a. Now, we're assuming now that a is non-zero because we've already dealt with the case when a is 0. So if a is non-zero, this series is clearly divergent. Yeah. So you're adding a plus a plus a plus a. So no matter how small a is, this is still going to grow without any bound. So it's going to get larger and larger and larger. In the positive direction if a is positive, or in the negative direction if a is negative. Okay, so this is clearly divergent. So these are all kind of special values of R, special values of the ratio R that we're dealing with. Here's another one. If R is -1, then you see if R is -1, you're doing A plus AR squared plus AR cubed. Well, R to some integer power is just going to give you +1 or -1. And it alternates between +1, -1, +1, -1, etc. So the series looks like, the second one will be R, so it'll be A minus A, yeah, plus A minus A, plus A. So you're adding A, subtracting A, adding A, subtracting A, adding A, subtracting A. Again, this is kind of, it's not really a genuine, it's not really what we intend to study, but this again is a divergent series. I mean, it's certainly not growing without any upper bound, but the partial sums of this series alternate between A and 0. But we've assumed A is non-zero, so if the partial sums are alternating between A and 0, then they're certainly not converging. Okay, so it's a divergent series. So in this case, in the R is -1 case, we say the partial sums alternate between A and 0. So it's not a convergent sequence of partial sums, so therefore the series is not convergent. So those are just some special cases to get out of the way first. There's some easy wins, if you like. Easy values, not easy, but values of the parameters that we can just deal with immediately, okay? So now we'll tackle the general case. Okay, so now we can assume, so now we have A is non-zero and R is not equal to 0, -1, or 1, say. And now we'll deal with all of the remaining cases. We'll just deal with in a single kind of argument, okay? But in order to do it, we want to obtain a nice formula for SK, the partial sum of this series. So this is the sum from n equals 1 to k of AR to the n minus 1. So this is A plus AR squared. But this time it ends. It ends with the final term A times R to the, that'll be times R to the k minus 1, won't it? Because when n is equal to k, you'll have A times R to the k minus 1. So this is the partial sum of the series. And remember, we defined convergence for the infinite series as what convergence for the series meant was if the sequence of partial sums converges, okay? Now, we want a nice formula for this. At the moment, we don't have that. So at the moment, we've got a kind of indeterminate number of terms here. Really, this is just the instruction to add up all these terms. So there's a ... in the middle. It's a bit unspecified. So it's hard to do any analysis or algebra of this. But if we can simplify the situation, if we consider also the quantity R times the partial sum. So if we multiply the partial sum by R, what we'll get is, and I'll just shift everything to the right, you see you get, well, no, I'll just leave everything in place. AR is the first term, then you have AR squared, and then you have AR cubed, and so on. And then you end with AR to the K. So what we're exploiting here, we're exploiting here the similarity, or we're exploiting the geometric nature of the terms. See, because now we can subtract these two equations from one another. See, most of the things up here are the same as the things down here, most of them. So if we subtract the bottom equation from the top, almost everything will cancel out. And we'll just be left with two things and no longer an unspecified number of terms. So if we subtract them like this, on the left-hand side, we'll have sk minus rsk. And on the right-hand side, so we're subtracting the bottom from the top. So AR cancels with AR here. AR squared cancels with AR squared. There's going to be an AR cubed there. That will cancel with that. And the AR to the k minus 1, that cancels with the second last one here down the bottom. AR to the k minus 1. So almost everything cancels except for these two bits. You got an A at the front, and you'll have a minus AR to the k at the bottom. Okay, because you're subtracting the bottom equation. Now this is much nicer now because we don't have the dot, dot, dot in the middle of our expressions anymore. So we have a much more definite description of this. And we can do a little bit of algebraic manipulation here to just factorize this like this. Okay. So the left-hand side factorizes as sk multiplied by 1 minus r. And then you can bring the 1 minus r over to the other side and factorize out the 8. So this is what we meant by nice formula. So when I said we wanted a nice formula for sk, I meant this one. And there's a nice subtraction argument which gets us to it. And this is the one which we can examine the convergence of. Okay, we're trying to settle the convergence of the series, and we can do that by examining now the convergence of the sequence of partial sums. Okay. So how does sk behave as k tends to infinity? That's the question. And notice as well that there's no problem with dividing by 1 minus r. Normally, if you were doing algebra and you divided by 1 minus r, you'd have to worry about, well, what about if r is equal to minus 1? Because then you'd be dividing by 0, which you can't do. But of course, r is not minus 1 because we set up here somewhere, yeah, we're assuming now that r is not minus 1. Because we've already dealt with the case of r equals minus 1. So there's no problem with dividing by 1 minus r. So how does this behave as k tends to infinity? Well, the only place where k is here is in r to the k. So it comes down to how r to the k behaves. And now you can see where the conclusion from the statement of the theorem comes from. If r to the k is less than 1, sorry, if the absolute value of r is strictly less than 1, then r to the k, see, when you take something strictly less than 1 and you raise it, when you square it or cube it or fourth power it, it gets smaller, doesn't it? Because you're rescaling by r, so you're going closer to the origin. So this is going to go to 0 as k goes to infinity. Whereas if the absolute value of r is greater than 1, well, if you take something greater than 1 and square it or cube it, multiply it by itself, because it's greater than 1, it's going to scale outwards from 0. If it's positive, it'll just get larger and larger. If it's negative, it'll get larger and larger in absolute value, and it'll be all hopping either side of 0, but getting larger all the time. So you could say just simply that it diverges as k goes to infinity. So by the algebra of limits theorem for sequences, you see r to the k is the only place where this depends on k. All the other parts of the expression are constants. We can say if the absolute value of r is less than 1, then the limit as k goes to infinity of sk is equal to a over 1 minus r. Okay, because the r to the k will converge to 0, and you'll just be left with a times 1 over 1 minus r. And if the absolute value of R is greater than 1, SK diverges. So this is the as required. That was what we were required to prove. That was what the theorem said about these geometric series. So the things to note in that, okay, we dealt with some easy cases at the start, special values of the parameters where we could just tell by inspection what was going on. But dealing with the general case, okay, we had this nice subtraction argument to get to this nice formula for the partial sum, but then we made use of the definition of convergence for a series. So we're examining the limit of the sequence of partial sums. And then also, crucially, we used a previous result, this algebra of limits theorem for sequences, this result back in chapter 1. So we're always calling back to and making use of previous results. So that's the end of the proof there. So any questions about that or things that I could clarify for you on that? Is that okay? So it's a nice piece of analysis, and it's kind of rare for these convergence tests that it gives such a complete description of everything that can happen with a geometric series. Okay, so in principle now, if we're presented with any geometric series, we should be able to say what happens to it. Okay, so let's look at some examples. Everybody finish with that page? Yeah. Okay, let's look at a couple of examples. Let's look at two. First of all, let's look at, so what's going on with this series, a fifth plus a fifth squared plus a fifth cubed, etc., etc. And maybe the second one, say the sum from n equals 1 to infinity of, say, this one. A bit odd, but this series here. Maybe let's try another one. Sum from n equals 0 to infinity of minus 4 to the 3n by 1 over 5 to the n minus 1. Let's try this one. Okay, so it should be, or at least it's suggested that these are all geometric series. So we should be able to apply the geometric series test to them. But, you know, maybe the form of the expression changes slightly. So initially, we're going to have to try and translate these descriptions back into the description that's given in the theorem. So we'll want to identify the A and the R, the appropriate A and R for these series over here. Okay. So we'll look at number 1 so far. Well, this is perhaps the most straightforward one. You can see what the initial term is. Remember, A is the initial term of the geometric series. So we have A equals a fifth. And R is a fifth as well, because each term is obtained from the previous one by multiplying by a fifth. You've got a fifth squared, a fifth cubed, and so on. So we know what A and R are, so we should know the complete story, okay? So here, clearly, the absolute value of a fifth is clearly less than 1, so it is convergent. And the sum from n equals 1 to infinity of 1/5 to the n. We can write it like this. So it's a over 1 minus r. So it should be a fifth over 1 minus 1/5, which is a quarter. 1/5 over 4/5, so that will be a quarter. Okay, so it's clearly convergent, and we can see straight away what the limit should be. So, okay, any questions about that? So once you know the a and the r, you just examine the r. Is it less than or bigger than 1? If it's bigger than 1, it's going to be divergent. If it's absolute value bigger than 1, it's going to be divergent. Otherwise, it's going to be convergent, and we can grab the formula for the limit, a over 1 minus r. So let's look at example 2. Now here, things are a bit more mixed up. There's 2 factors which are both raised to exponents which have an n in them, but it's not exactly the form of the theorem here. So it's a bit harder here to identify the a and the r. So that's what we're going to try and do. So here's the series we're dealing with. The index goes from 1 to infinity, as it does in the statement of the theorem. So we'll leave that alone. So we got 9 to the minus n plus 2, 4 to the n plus 1. Well, first of all, we want the index to be n minus 1. So we want the index to be 1 times n minus 1. At the moment, we got a minus n here. So if we'll leave the 4 to the n plus 1 up here and bring the 9 below, so it will be n minus 2. So we're just changing the sign of the exponent and putting 9 below the line. And then just drifting back here. Now we want to get these exponents to be n minus 1. So I need to take 4 squared out here, and that will leave me with 4 to the n minus 1. And I want to leave 9 to the n minus 1, but I want it to be n minus 2, so I better have a 9 to the minus 1 there. So here I've pulled out this constant, seems to be 16 times 9. It's 126. 16 times 9, 126. Yeah, thank you. And then that's 4/9 to the n minus 1. Now, success. So examined it, shoved stuff around until we've got it looking like the form of the geometric series in the theorem. Because now you can see clearly this is the sum from n equals 1 to infinity of an a times an r to the power n minus 1. Okay. So we have a equals 126, that's the initial term, and r equals 4/9 in the notation of theorem, whatever it is. What's that number? Theorem 2.4. So if you're presented with something, if the formula is just a load of factors raised to powers involving n, it's going to be geometric, and it might just take some persuasion around to get it into this standard form. This, if you like, is our standard form for geometric series, because that's the one that's discussed in the theorem. Now, of course, is this converging or diverging? Well, the 4/9 is clearly absolute value less than 1, so it's convergent, and we've got our a and r, so we can just calculate the sum by doing a over 1 minus r. So this is convergent since 4/9 is absolute value less than 1. And the sum of it is going to be, it's 126 times 4/9 to the n minus 1. It's going to be a, which is 126 over 1 minus 4/9, which is, what is it, 9 by 126 over 5, which is whatever it is, some number. But it's convergent, and there's the limit of it. Okay? Yeah, I mean, sometimes with difficulty, but yeah. I mean, well, let me correct what I said. If it's a collection of factors where the indices are linear expressions in n, so maybe some multiple of n plus some constant, which these are. So here we have a -1 times n plus a constant. I mean, if you ever see n squared or n cubed, then that's not going to be geometric. But series where the terms can be factorized into things where the exponents are linear functions of n, and the bases of the exponents are constants, then that will be geometric. And you just keep hammering away at it long enough, get it into this prescribed form. So you see an a and you see your r all raised to the power n minus 1. Yeah? Possibly. Well, you tell me. So where did 126 come from? 16 times 9. So it's 90 plus 54. Yeah. So what was I thinking? 144? Okay. So, you know, don't hesitate to leap in and correct me. Should have done it earlier. But I think I did 9. I did 9 times. Oh, I don't know what I did. I think I said 9 times 6 was 36 in my head. Poor show, anyway. Okay, so let's try this one. Let's try the third one. We have a third example there. Now, this is now becoming, you see, I've got various things to various powers. And look, see, just watch out for that. The indexing is not starting at 1 now, it's starting at 0. So this is kind of obfuscating things or making things difficult almost on purpose. But it's a good exercise with algebraic manipulation and use of notation to figure out what the standard form of this geometric series is. It is a geometric series. I think it is anyway. But the question is, what does it look like in our standard form? So we want to convert this to sum n equals 1 to infinity, and we want to see what the a is, see what the r is. Okay, so we need to identify the a and the r, because then we can do this formula a over 1 minus r. Well, okay, so what are we going to fix first? Well, let's fix the index first. So what happens if I just decide I'm going to start the indexing at 1 instead? I mean, how can we handle that? Yeah. So we could just leave this as, we could leave the formula here the same. Yeah. But just separate off the n equals 0 term. Yeah, that's a good way to do it. So when n is 0, it's got minus 4 to the 0, which is 1, over 5, 1 over 5 to the minus 1. So that's the same as 5, isn't it? So it seems to be just 5. Okay, so that's one good way. Just take that extra term, that 0th term, and just separate it out. The other way I was thinking of although I'm going to run with this one. You see now we've taken our geometric series and says, well, we've extracted a constant out of it and replaced it with another geometric series. So now we're just going to examine the convergence of this one. Obviously, if the original series is going to converge if and only if this series converges, yeah? Because this one is equal to this one plus 5. So if this one is going to come to a limit, so will this one. But if this one diverges, then so will this one. Okay? Having a constant difference between the two doesn't affect convergence or divergence. The other alternative way to do it, I'm going to go with this way, but the other way you might have done it was to insist you're going to have n equals 1 to infinity, but then subtract 1 from the n in the index positions up here. So instead of minus 4 to the 3 times n, it's 3 times n minus 1. See, because that will have you first do, when n is 1, you'll have minus 4 to the 3 times 0. And then minus 4 to the 3 times 1, which is how this one started off. And instead of 5 to the n minus 1, you'd have 5 to the n minus 2. So that'd just be another way of doing it. Just be another way of doing it. If you follow that route, you should reach exactly the same conclusion. Okay, so then we just have to make all these indices minus 1. Well, the fifth is already minus 1, so that's good. Now, how do I deal with this? Well, of course, I use this other property that I can write this like this. Okay, minus 4 to the power 3 times n. Of course, when you've got products in the, isn't that right? Yeah, products in the exponent, that's just the same as taking, composing the exponents. Okay, so you can bring the cubed inside. I do know 4 cubed is 64, so minus 4 cubed would be minus 64. So this is oh, I've still got the plus 5. Minus 64 to the power n over 5 to the n minus 1 plus 5. So finally, this is 5 plus. So we need to take one of those 64s out. And then we'll be left with minus 64 over 5 to the n minus 1. Oops, don't see that. That makes sense. So finally now I've got it in standard form, because here's my a, and there's my r to the n minus 1. So, divergent or convergent? Should be able to tell, because there's our a and r, so divergent. Because the r, the common ratio is 64 over 5, or minus 64 over 5, so it's clearly a bit bigger than 1. The fact you're adding on 5 to it isn't going to change the divergence or convergence of it. Yeah? If this is growing without upper bound in absolute value, as it's going to be now, adding on 5 to it isn't going to change that behavior. The 5, so yeah, so where did the 5? The 5 came from, see, in the original form, the indexing started at 0. But to match it to the standard form, the indexing begins at 1. Yeah? So the first term of this is when n equals 0. So we just separated that off completely and put it over here. Now, when n is 0, you've got something to the 0, which is 1, divided by 5 to the power minus 1. So that's the same as multiplying by 5. You got 1 over 5 to the minus 1, so it's 5. So it's 1 times 5. So 5 is just the initial term of this series. But we just peeled that off and left it to one side. Then the indexing begins at n equals 1. Yeah? Which we can then continue to make this look like our standard form up there by working it so I can see the a and I can see the r. Okay? Yeah? So clearly here, So the absolute value of minus 64 over 5 is clearly strictly bigger than 1. So this is a divergent series. The a over 1 minus r doesn't come into it because it's divergent. So is that okay? Any queries on that or further clarification I could give? Okay, I think we're making good progress with these, so I won't rush ahead and do another one today, but just to give you some suggestions for the tutorials, if you go to the end of chapter exercises there, on page 18 and 19, I think everything up to question 4 should be available to you there. And question 6 is available as well. So everything to question 4. Maybe skip question 5 for the moment, but also question 6.